Hi, I'm Terry O'Toole, and today I'll be talking to you about Three.js and interactive 3D rendering. Most people are familiar with these concepts from video games, where there's a 3D digital environment that the user can move around and interact with in a bunch of different ways. The Three.js library allows you to make and render these digital spaces inside the browser using JavaScript. The library is available on GitHub under an MIT open source copyright, so it's available to everyone for free. It was initially released in 2010 by Ricardo Cabello, or Mr. Doob on GitHub. It was intended as an easy-to-use, lightweight 3D library. It's built on top of Mozilla's now ubiquitous WebGL API, which they released in 2011. Three.js took off as one of the most commonly implemented in-browser uses of WebGL. And essentially, Three.js is an abstraction over it. And also, since WebGL is what's used in almost all mobile devices, Three apps are naturally platform agnostic. Three.js is so powerful because it can be implemented simply from inside of an HTML canvas element, and through WebGL is powered by the GPU. Modern screens refresh at 60 frames per second. So in order for our 3D environment to change and animate, we need to re-render every pixel every 15 milliseconds. So we need to use the GPU because it is formatted to handle huge amounts of data and perform the same repetitive operations over it. CPUs simply aren't built to handle the amount of data that we have to manipulate at a constant rate. So just how big is this data? Well, one typical 40-watt light bulb produces 10 to the 19th photons per second. That's 10 quintillion photons. And it's estimated that in order to accurately calculate all of the photons emitted from one 40-watt light bulb in real time, it would take all of the computing power in the world times 10,000. So obviously, we won't be doing any calculating on nearly that scale. But there is still an incredible amount of data, or an incredible amount of information to render with each frame. So that's why engines like WebGL have devised specific techniques to reduce the number of calculations. So let's start to talk about setting it up. This is where we'll start to look at how Three.js is implemented. There are 5 essential things that I'll be going over that you'll need in every single Three application in order to begin the render. If any of the 5 are not there, you won't be able to see a scene, and it won't render at all. So first are the scene object and the render function. In the JavaScript on the right side of the screen, in the very first line, we initialize a new Three scene. Everything we want to add to the virtual environment needs to be added to the scene object using scene.add. The object is then passed into the renderer at the end of the script, as you can see. The scene object is what actually creates a 3D space. It's defined by a Cartesian coordinate system with x, y, and z dimensions. So after defining the scene, we'll need to initialize our renderer function that uses WebGL. And then we need to append the rendering canvas element onto the DOM, which is just a simple injection of a canvas element, and that it'll continually refer to throughout the rendering process. The renderer.render function will be called every single time the frame updates, so every 15 milliseconds. This is what is going to send our scene elements into the GPU for rendering. Cool. So now that we have a scene and a renderer set up, it brings to our second of the Three.js essentials, the camera. The camera basically takes every pixel on the screen, and for every frame, sends out a ray from this nearest camera plane out into the scene. At the first place that those rays hit a surface, it looks at the material, texture, and environmental lighting to determine what the color of the surface should be. This happens every single frame for every single pixel. In order to initialize it, you'll need to set the nearest and furthest distances from the camera that the camera can see. So those 2 planes create the camera frustum. That's the name of the triangle pyramid shape. That way, only surfaces that are both inside of the frustum and facing the camera are going to be sent to the GPU. Nothing else is sent to the GPU. We have to keep the data as limited as possible in order to keep it going. So what are our options for cameras? There are two different types of them. The first is a perspective camera that mimics the way that the human eye works. This camera gives you lines that converge in the distance, and it's used in most 3D style video games. It's implemented in Three.js and added to the scene, as you can see in the top right, where we have the scene.add camera. Like I said before, if we don't use that function, it will not be brought into the 3D environment at all, and we'll have no way to view the scene. Our second option is the orthographic camera. This is mostly used in side-scrolling and 2D style video games, and instead of sending out rays from a small plane to a larger one, they go straight from one plane to another one of the exact same dimensions. This way there are no focal points and no converging lines in the distance. It's added to the scene in the exact same way as the previous camera. Cool, so now that we've chosen one of the cameras and added it to our scene, we can begin to add geometry to our Three.js, which is our third Three.js essential. All right, so geometry allows us to manipulate the scene very precisely. In this example, we can define 3 points that are called vector threes by their x, y, and z coordinates in space, and then push them onto a vertices array within the geometry element. Then we can create a face by taking the first three vertices of the array and pushing them into a new face array that's also on the element. All geometries are broken down into triangles like this. The only things that we ever want to send to the GPU are points or vertices, edges, and triangles. These triangles can then be combined to make any shape you want. For instance, the teapot, which is, this is essentially like the hello world of 3D models. Surprisingly to some, both of these teapots use the exact same amount of polygons. There are shading techniques that allow us to make any polygonal surface look smooth the same way that curves would. And as a small note, modeling with curves instead of points and faces is possible, but it's outdated since we can now very easily make any polygonal surface look smooth. Cool. So 3 comes with about 20 primitive geometries that can be generated directly from the library. These are the building blocks of most 3D programs. And they're defined by simple constructor functions and are fairly straightforward to set up. All you need to do is initialize it with the correct variables. So here we have a box, a torus, and a dodecahedron. Other primitives include things like planes, cones, cylinders, spheres, and other 3D and flat polygons. More complex geometries can be loaded in by our good old friend, the JSON object. These files are converted using some of 3's dev tools that come with the library. And they're converted from .fbx and .obj files, which artists use to build and edit the actual objects. You can see at the top of the JSON object that the geometry is defined using an array for creating the vertices and then another array for creating the faces, exactly the same way that we had done it by hand a couple slides ago. Cool, so now that our geometry is set up, we can start to move on to essential number 4, materials and textures. Materials are what determine the color of the geometry and how light interacts with it. When materials are combined with the geometry, that object is now called a mesh. So the two of them together are a mesh. When it's just a shape, it's a geometry. Recently, renderers have moved away from using like multiple different types of shaders to using like one single physically based shader is what they're called, like the standard material that you see here. They're meant to mimic real world materials and use more semantic words like metalness and roughness instead of specular and anisotropy. So things with a low roughness are smoother, creating a shiny, more polished surface, whereas materials with a high metalness can alter the way that light reflects off of them, creating just a more overall metallic look. But say instead of using just basic materials, we want to use an image to color our geometry. So separate from materials, but very closely related, are textures. To add a texture to each geometry, each thing must be given a second set of coordinates. This is called a UV coordinate system, where like U is X and V is Y. In this space, you like unfold your mesh into a flat plane, and then you can map a 2D image to it. This step is almost always done by the creator of the object. So as a developer, you wouldn't necessarily be doing this. Not all objects are UV mapped, and a lot of them just don't need to be UV mapped either. It's also worthwhile to note that you will still need a main material even if you have an image texture. You always need a material, you do not always need a texture. Now that we can map our images to our geometries, we can do some very interesting things with it. This torus knot has 3 different images mapped onto it that each do different things. A color map or a diffuse map that dictates the color of the surface, a bump map that changes the way light bounces off the surface, and a roughness map that changes how the light is reflected off of the surface. In combination, they can make really photorealistic looking graphics, but if you have to download 3 images for each geometry, it's going to put a lot of strain. It'll take a lot longer to load. There's one more essential thing missing before we can see a scene displayed on screen: lighting. Lighting is what allows you to see the scene. Without it, the renderer will not be able to calculate the color of any of the materials. The renderer will start, and you'll be looking at a black screen and wondering why it isn't running. And I know because it's happened to me a bunch of times before. There are 4 basic types of light that we'll go over, but there are a couple other ones there. The first 2 are ambient and directional lights. Ambient light is the simplest kind of light. It globally illuminates all objects in the scene evenly. The light cannot be used to cast shadow, and it does not have a direction. It's totally ubiquitous. It just gives the entire scene an even coloring. Directional lights are lights that come from a specific direction, but has no single source. It mimics the sun. It basically works the same way that an orthographic camera does, where all of the rays come in one direction straight to the bottom. Point lights mimic light bulbs. They emit light out in all directions from a single point and can cast shadows, and as you can see in the example video. And finally, we have spotlights, which emit light from a single point in one direction, creating a cone shape. And they also can produce shadows. Speaking of shadows, if you want them, you need to turn them on for each light you want to cast them. By default, they're off because shadows are one of the slowest and most expensive things to render. Shadow maps use a ray tracing function the exact same way a camera does, basically. They emit rays from a source and illuminate only things that the light can see. So in many video games, shadows are normally baked into the image texture map. That way, they're not dynamically created, and it takes a lot less strain off of the GPU renderer. So it's recommended that if you are using a shadow map, you make it as small as possible. The default is 512 by 512, and that generally can keep render times pretty low. So again, here are the 5 essentials that you need in order to get started working with Three.js. A scene and a renderer to set up the environment, a camera for us to view it, mesh geometry with materials and textures, and lighting to view everything afterwards. Apart from these 5 things, which are the absolute most basic, Three.js gives us a ton of different additional functionality that allow you to build out really interesting looking scenes that do some really crazy dynamic things. And it works really well with other plugins. So there are a couple more resources. Three.js.org is one of the most fun websites. You could go click around and just explore everything. The documentation is all right, but where its strength is that it gives you different example codes for every single function that's available in the thing. So it's really easy to do that. And there's a couple other really great resources for you out there. So thank you, everyone, for your time.